All right. Good afternoon, Ray, Carlo, and Adriel. So before we start today's discussion, just housekeeping matters. Tama nga ba? I promised to give you the uh, the last problem set for the course on December 16. Siya yung huli ko nakita rito sa course guide natin. And then it will be due on December 24, right before midnight. But of course, if you don't want to work beyond the last day of classes, which is on the 21st, pwede nyo namang ipasa siya by December 21. I just gave additional days just in case medyo nagpatong-patong na yung mga hinihinging problem set or final assessments for you in other classes. So siguro we can lay back a little bit and relax as far as 155 is concerned. So I can accept submissions without any deductions until December 24th, right before midnight, bago tayo mga mag-Noche Buena. And then we still have a final output, a final exam, which will be due on the finals day that is assigned to us by the registrar. But I guess I promised that the earliest deadline that I will impose would be January 7. So if the final exam will be scheduled for Math 155 is on December 5 or January 5 or 6, imumove natin yung deadline by January 7. Because as I have mentioned, yung final exam is doable in less than a day. So pwede nyo siyang gawin. Nag-promise nga ba ako na ibibigay ko siya by ibibigay ko siya earlier than or before we go to the Christmas break? Para kung gusto nyo talagang tapusin yung 155 before January, so posible. Hindi ko matandaan kung pinramis ko yun sa inyo or hindi. But just let me know if you want to do it that way. I can give it by December 21, probably. And then it will go live on Canvas. You can submit anytime during the break until the deadline, which is January 7 at the earliest. And at the latest, dun siya papasok sa last as a schedule ng final exam for Math 155. But the earlier the better para mo-compute kagad yung final grades niyo sa Canvas. Doon yun siya makikita yung final grade. Kung ano yung i-output ni Canvas as your final grade after you submitted all the requirements, then yun na yun. You can ask for clarifications, pero hindi ako magko-compute mano-mano. So kung ano yung lumabas kay Canvas, siya na yung isusulat ko sa grade sheet. All right? Unfortunately, medyo napasarap yung bakasyon ko. So I was planning na during the evening, kung wala nang mga ganap dun sa vacation ko last time, I should have started grading problem set number 3. But unfortunately, hindi ako nakahanap ng free time. So I'll try to grade problem set number 3 probably over the weekend so that you get immediate feedback for it. Hopefully by Monday, you will get your scores in problem set number 3. Okay? And I guess we are now on the last hurrah for Math 155. We were talking about integration or the generalization of the concept of integrals for at least the set of real numbers or over subsets of R. So we already talked about the Riemann integral, but there are certain other topics left. Ngayon, papahapyawan natin yung integrating functions with discontinuity, but I think you already know how to do it from Math 36, so just formalize things. And then we'll talk about properties of integral probably next time. And then these are some important results that we'll be looking at. Although we already, today we will talk also about criteria or some ways to check whether a function is Riemann integrable or not, okay? So hindi ko lang sure kung maabot natin yung Lebesgue's criterion, but let's see, okay? So far, we're still at pace to finish the course without introducing any other additional classes or recordings, but let's see. Meron lang nakita dun sa worksheet dito sa lecture notes siguro mga 2 minutes ago na medyo may problema. So, or hindi pala 2 minutes, 4:08 na pala. 2 minutes before time napansin ko na may konting problema dun sa isang proof dito sa lecture notes. So, I wasn't able to remedy it right on time before I went live. So, baka i-defer ko na lang yung proof So, or I will resupply it to you and it will be assigned as a reading assignment. Okay. But I'll promise you that I'll include all of the details in the proof. I'll write it myself kung hindi ko man siya madidiscuss together with you. All right. Now, since it's been a long time since we saw each other, siguro it's a week since we last met. So balikan natin ano yung na-discuss natin about the Riemann integral. So sa Riemann integral, nagko-consider tayo ng isang function defined on, say, an interval AB, and we want to look at how to develop or how the Riemann integral of f, when we say Riemann integral, ito yung definite integrals mula sa Math 36 ng isang function f over the interval AB. Paano to kino-compute, right? Without going through the concept of the antiderivative. Kasi nga, tinry nating paghiwalayin yung konsepto ng derivative at integrals. Though we know the first fundamental theorem of calculus, which serves as a bridge between derivatives and integrals. Basically, ang sinasabi ng first fundamental theorem of calculus, ang differentiation ay inverse process ng integration and vice versa. But one can develop differentiation theory and integration theory independently. And that's what we are trying to do here. All right. So in our development of the Riemann integral, we went through defining a partition inducer of an interval AB. So we say that a set P consisting points x sub 0, x sub 1, until x sub n is a partition inducer of the interval AB if x sub 0 is equal to A, x sub n is equal to B. So dapat sila yung endpoints. Tapos ang isang partition inducer ay isang ordered set so that x sub 0 is less than x sub 1, x sub 1 is less than x sub 2, and so on until x sub n minus 1 is less than x sub n. So ang idea ng isang partition inducer, meron kang interval AB, siya yung gagawa ng isang partitioning ng set AB. Remember, ang partitioning dapat ay disjoint sets. All right? So dito makukuha natin ay disjoint intervals that will add up, or that whose union will give us the set AB. All right? So ito si x sub 0, ito si x sub 1, ito si x sub n. Diba, meron kang x sub 1 dyan. Tapos si x sub 1 dapat mas maliit kay x sub 2. Si x sub 2 mas maliit kay x sub 3. Si x sub 3 mas maliit kay x sub 4, and so on. So kung ito yung mga elements ng partition inducer, so I will have the following subintervals. First subinterval I1 from x sub 0 to x1. Second subinterval x1 to x2, that's going to be I2, and so on. The union of the closed interval versions of I1, I2, I3 until In will give us the entire interval A comma B. All right. And then we defined the concept of upper and lower Riemann sums induced by a partition inducer. Parang doble-doble na, no? Induced by a partition inducer. Pero pag meron kang, pagkukompute mo yung lower sum or lower Riemann sum ng isang function f relative to a partition inducer P, siya lamang yung sum ng mga areas ng mga rectangles over the subintervals induced by P, wherein the heights of each of the rectangles will be determined by the infima, or in our case, the minima, ng mga function values sa bawat subintervals. So kukunin natin yung pinakamaliit na value ng f of xi, or ng f of x sa interval x sub 1, sa interval x sub 0 hanggang x sub 1, i-multiply ko to by the width of the interval, all right? And I'll do this for all elements of all subintervals created. So this would be from 1 to capital N, because we will have n intervals if we have n plus 1 elements of a partition inducer. So ito yung lower Riemann sum. And I think we illustrated this before na, okay, itong lower Riemann sum, ito yung mga maliliit na posibleng sum ng mga areas ng mga rectangles. Bakit sila yung pinakamaliliit? Kasi ang ginagamit natin na height nung mga rectangles na pinag-a-add natin yung mga area ay yung infima. Sila yung mga pinakamaliit na function values over the subintervals, so you can think of it as summing the areas of the smallest rectangles that can be defined over each of the subintervals. All right? And that is in contrast to the upper Riemann sum of f relative to a partition inducer P. So dito naman, kinukuha pa rin natin yung sum ng mga areas, pero yung ginagamit kong height para sa bawat rectangle ay si capital M sub I, which will stand for the suprema of the function values over each of the subintervals. So pipiliin ko sa subinterval I sub j, okay? Sa pagitan ni x sub j minus 1 at ni x sub j, ano yung pinakamalaking function value? Yun yung gagamitin kong height ng rectangle na ipapang-approximate ko sa area ng region bounded by the function over that subinterval. All right? Of course, it would be larger than the actual area kasi ito yung pinakamalaking rectangle na pwede kong mabuo sa isang subinterval. So basically, if you want to get the actual area, which may back knowledge na kasi tayo sa Math 36 na yung area ng region na yon, siya dapat yung definite integral. Pero sabi natin, capital L will be an underestimate kasi nga kinukuha natin yung pinakamaliliit na posibleng rectangles, while capital U or the upper Riemann sum would be overestimation of the area of the region because again, we are considering the largest rectangles possible over each of the subintervals. So we want them to meet in the middle. Hindi ayoko ng masyadong underestimate, ayoko ng masyadong overestimate. All right? And the trick there in getting to the middle and getting the exact area, all right? Sa Math 36, ang sinabi, kukunin natin yung limit. Paparamihin natin yung mga subintervals na ginamit. That will result into thinner and thinner rectangles. Pero ang kagandahan nun, yung height na mapipili natin is a good representation of what the actual height over that subinterval is. And when we sum up the area of those very, very thin rectangles, makukuha natin yung area ng shaded region exactly. Pero that involves concept of limits. Ina-avoid ko ngayon yung paggamit ng ibang mga konsepto other than elementary principles. All right? So, ang idea ay masyadong maliliit yung mga lower sums. Masyadong malalaki yung mga upper sums. I want them to meet in the middle, and for that, I will take, for instance, gusto kong palakihin yung mga lower sums, pero ayoko silang palakihin ng sobra. So, kukunin ko na lang yung least upper bound ng mga lower limits. So, kukunin ko yung kukunin ko yung supremum, which is the least upper bound ng mga L of FP, ng mga lower sums of F relative to a partition P over possible partition inducers P. So, kukolektahin ko lang lahat ng posibleng partition inducer, capital P, kukomputin ko yung lower sum nilang lahat, tapos kukunin ko yung least upper bound ng mga lower sums na yon. And that is what I will call the lower Riemann integral of F over the interval AB. Okay? So, kumbaga, nandito yung mga capital L, L1, L2, L3, L4. Yan yung mga lower sums, kaya lang maliit sila. Halimbawa, ito yung eksaktong area, maliliit sila kaysa dun sa actual area. So, gusto ko siyang i-force na pumunta somewhere in the middle. So, papalakihin ko yung mga lower sums pero hindi siya dapat lalampas doon sa actual area. Kaya kinukuha ko yung supremum ng mga lower sums. Okay? Now, I'll do the analogous thing for the upper sums. This time, masyado namang malalaki yung upper sums. They represent overestimations to the actual area of the shaded region. So, kailangan ko silang paliitin ng konti. Alright? So, ngayon, titingnan ko, ano yung lahat ng possible partition inducers. Tapos, sa bawat partition inducer na yon, kukunin ko yung upper Riemann sum. Tapos, kukunin ko yung greatest lower bound kasi sobrang malalaki nga yung mga upper sums. Kukunin ko yung pinakamalaking lower bound nila para mapapaliit ko siya pero hindi ko siya masyadong papaliitin. Right in the middle lang siya maninirahan. Alright? So that's how we define the upper Riemann sum. The upper Riemann sum is the infimum between or among all upper Riemann sums. And that's what we'll call the upper Riemann integral of our function f. Okay? And then after we developed these things, we said, okay, we say that a function little f is Riemann integrable if and only if the lower Riemann sum is equal to the lower Riemann integral is equal to the upper Riemann integral. Riemann integrable siya kung nangyari yun. That's our definition of Riemann integrability. And moreover, the common value between the lower and upper Riemann integral is what we will call the Riemann integral of the function f. All right? But you will see it's very tedious on how to check whether a function is Riemann integrable because it will take us to consider all possible partitions or all possible partition inducers for the interval of integration AB, compute all the corresponding lower and upper Riemann sums, compute their supremum and infimum, compare the two values. That is a lot of work, all right? Pag binigyan nga tayo ng isang function, ang hirap ng isang sequence, ang hirap hanapin ng supremum at infimum nila. What more, if we will consider getting all the possible partition inducers, which is actually, I don't think it is a countable set. So napakarami ng mga posibleng partition inducers. All right? So that's why we need to develop some easier ways on how to determine Riemann integrability. And on our way there, we need to establish one nice inequality, okay, which will prove to be useful later. And I think doon tayo tumigil. Sinabi natin na, okay, ito ay isang magandang inequality. And we said na ito ay madali kasi yung lower Riemann sum ay supremum ng mga lower Riemann sum. So by definition, this is obvious. This inequality is also obvious kasi nga ito ay infimum ng mga u. So definitely this is a lower bound first for the u's. So that's trivial. And the challenge now for us is to establish this inequality na ang lower Riemann sum ay less than or equal to sa upper Riemann sum. Okay? And again, ang goal natin sa Riemann integrability, ipakita na equal itong dalawa. It would be a very great help if we will be able to demonstrate this inequality to be true. Kasi one route to check Riemann integrability will just be to check yung reverse inequality. Kasi kung true yung reverse inequality, kung nangyari na yung lower Riemann integral is shown to be greater than or equal to the upper Riemann integral, conjunct that with this statement, then we are sure that the lower and the upper Riemann sum are equal to each other. Okay? Kaya medyo maganda rin na i-prove natin ito para mabawasan yung kailangan nating i-prove kung dadaan tayo dun sa definition ng Riemann integrability. And then we could have written a straightforward proof for this inequality. Kaya lang ang ginawa dun sa textbook o dito sa lecture notes, hinati siya into several lemmas or lemmata, kung ano man ang ginagamit yung plural form ng lemma. So I think we were done with lemma 5.1. Medyo napahaba yata yung intro ko, already 21 minutes in. But yeah, yun yung problema ko pag nag-off script. So lemma 5.1, we were able to establish that this inequality, all right? So napakita na natin na ang infimum over the interval AB times B minus A is the lower bound for the lower sums, and the supremum all throughout the interval AB times the interval's length is an upper bound for all upper Riemann sums. And then this actually is obvious, right? So itong inequality na to ay nabuo. And then hindi naman ganun kahirap siya i-imagine. Si M yung pinakamaliit sa buong interval AB. Etong mga L's na to, na ang pinagsasum natin dito, yung mga pinakamaliliit na rectangles on each of the subintervals. So pag kinuha ko yung height to be the smallest all throughout the interval AB, that will be a smaller area than the area created, or the area or the sum of the areas created by rectangles taking the lowest function values on each of the subintervals as the heights. So I think yun yung naging argument natin when we proved lemma 5.1. And then I think we also defined what a refinement of a partition is. The idea, kaya siya tinawag na refinement, ay parang mas pino natin yung yung partitioning ng isang interval AB. Technically, we define a refinement P star of a partition inducer P if and only if, or by saying that it is a refinement if and only if P is a subset of P star. Ang idea niya kung bakit siya tinawag na refinement, kasi nga, halimbawa, ito yung partition mo, ito si P, ito si X0, ito halimbawa si X5, ito si X1, X2, X3, X4. So clearly, yung set containing X0 hanggang X5 ay isang partition inducer. It induces a partitioning of the closed interval AB into 5 subintervals, namely I1, I2, I3, I4, and I5. Yan yung 5 subintervals induced by capital P. Yung refinement ay isang superset, okay, ng P. Kukuha ako ng isang P star na superset siya ni P. Bakit siya tinawag na refinement? Kasi dahil siya ay superset, nare-retain yung mga original elements ng partition inducer, dinadagdagan lamang natin sila. So, posibleng may madagdag dito na pwedeng may madagdag dito na isang element. Paano ko siya tatawagin? Halimbawa, tawagin ko siyang X6. Kaya lang, hindi na siya magmamatter. Hindi masusunod yung ordering. Tawagin ko siyang X1 tilde. Alright? For lack of good notation. So, merong nasingit na element ng partition inducer doon sa bagong set. Kasi nga, naging superset. Nagkaroon tayo ng mas malaking partition inducer. So, that means the interval I1, which is supposedly from x sub 0 to x sub 1, might have been further trimmed down into a finer and smaller partition cells of the interval AB. Nagkaroon ng nakasingat na x1 tilde. So I1 was refined, quote unquote, into 2 smaller subintervals, x sub 0 to x sub 1 tilde and x sub 1 tilde until x sub 1. Yun yung effect ng pagdadagdag ng isang element dun sa isang existing partition inducer. Nagiging mas pino yung partitioning kasi yung isang original subinterval ay nahati into several other subintervals. All right? And then lemma number 2 or 5.2 will revolve around the idea of what is the relation between the upper and the lower Riemann sum generated by a refinement of a given partition inducer. Okay. So, burahin ko na to. Okay, para magkaroon tayo ng room to navigate here. Okay. So, lemma 5.2 says that if P star is a refinement of P, then these inequalities are true. The lower Riemann sum of F relative to P is always less than or equal to the lower Riemann sum of F relative to the refinement P star. So, ibig sabihin, mas malaki yung lower sums na nakukuha natin mula sa isang refined na partition inducer. But on the other hand, yung upper Riemann sum na nakukuha natin mula sa isang refined partition ay mas maliit kaysa sa upper Riemann sum ng isang partition. Okay? Tingnan natin bakit ganun yung nangyayari. Okay. So, mag-consider lang tayo ng isang possible subinterval. Halimbawa, nandito si A, nandito si B. Alright? Tapos kunin ko halimbawa, ito yung si xi. Tapos ito si x sub I plus 1. Baliktad, gawin kong x sub I minus 1 at saka si x sub I. Ito yung interval II. Tapos kunwari, ito yung function, f over the subinterval II. So originally, kung ito yung original partition inducer, okay? Tapos kukunin ko yung lower Riemann sum, alright? Para dun sa subinterval na to, kukunin ko yung minimum value ng function. So ito yung minimum value ng function over this subinterval II, alright? Tapos kukunin ko yung area ng rectangle dyan. ito yung area ng rectangle na yan yung idadagdag ko na contribution ng interval II para dun sa pagkuha ng lower Riemann sum ni F relative sa partition inducer P. Alright? So, tingnan nyo yung area na yan. Now, what happens if I introduce another element of a refinement or a refined partition inducer for the set for the interval AB? Kunwari, nag-introduce ako dito ng isa pang element ng partition inducer. Halimbawa, nadagdag ito, si x tilde I. Okay? So yung interval II, mahati siya sa dalawa. The first interval is from x sub I minus 1 until x sub I tilde. And then from x sub I tilde, papunta kay x sub I. Now, titingnan ko ano na yung magiging contribution mula dun sa original interval II dun sa lower sum. Pero ngayon, ang kinoconsider ko na yung lower sum dun sa refinement. Okay? Or galing dun sa refinement. Now, we will need to see what is the minimum value of f over the first refined interval mula kay x sub I minus 1 hanggang kay x sub I tilde. Alright? Kukunin ko yung pinakamaliit. I think nandito siya. So for this first refinement of II, ito yung gagamitin kong contribution. Alright? Tapos, mula dun sa pangalawang subinterval, mula kay x sub I tilde hanggang kay x sub I, kukunin ko uli yung minimum. Nandun pa rin yung minimum. So, ibig sabihin ng contribution mula dun sa second refinement of the interval II ay ito. And obviously, the area or the sum of the area of the orange regions is greater than or equal to, or actually here it's strictly greater than to the original yellow area that I have shaded before. So yung contribution mula kay II, dun sa original II, alright, mula dun sa refinement ng interval II ay mas malaki kaysa dun sa original contribution considering only II as a single interval, according to the original partition inducer. And this will happen whenever you insert a new element of the partition inducer. So kung sa isang interval II, nagdagdag ka ng isang partition inducer element, all right? So mas lumalaki yung contribution ng original interval. So that makes the lower Riemann sum, kasi isa-sum up ko yan, right? Pag nag-sum up ako ng mas malalaking areas, definitely the lower Riemann sum will be greater than or equal to the original Riemann sum. And I guess my geometric argument is encapsulated here. Okay? And similarly, ganun din naman kapag ka upper Riemann sum. Kaya lang mas mas lumiliit. Alright? Bakit siya mas lumiliit kapag ka nag-introduce ako ng isang partition inducer o isang bagong element ng partition inducer? Okay? Now, tingnan natin yung upper Riemann sum. The upper Riemann sum is from the maximum value, and I think the supremum is over here. Doon sa original, kulang. Sorry. Mukhang dito, okay. Drawing ko lang siya. Yan, kunwari yan yung maximum. Excuse me, guys. Okay, before the refinement happened, yung contribution ni interval II ay itong orange region. Pero pag nag-introduce ako ng isang panibagong partition inducer o isang bagong element ng partition inducer, and that happened to be on the interval II, may madadagdag dyan na isa. Alright? So, ibig sabihin, mahati siya sa dalawang subintervals. Alright? Sa x sub I minus 1 hanggang x sub I tilde, kukunin ko yung maximum. Ito pa rin naman yon. Okay? So, ito yung magiging contribution niya. Okay? Kulayan natin siya ng green. Tapos, dun sa x sub I tilde hanggang x sub I, kukunin ko ulit yung maximum function value. Kaya lang, yung maximum function value na sa kanya ay yung andito. So yung rectangle na i-contribute nung refined member nung partition ay eto na lang. I'll color it green. Eto na lang. And obviously, the green area is smaller than the orange area. So parang ngayon, dun sa refinement, mas maliit yung contribution nung interval I kesa dun sa original contribution niya prior to adding x sub I tilde. Alright? Kaya mas lumiliit yung upper Riemann sum kapag ka nagdadagdag ka ng partition inducers. Kasi parang namamanipula mo yung pagiging maximum ng isang element over the interval. Kasi kung consider ko to as a single interval, ito yung representative ko kasi ito yung maximum. Malaki yung rectangle na mabubuo ko. Pero pag hinati ko pa siya sa dalawa, ito, magiging height na lang siya nitong interval na to. And then, ang magiging height na nung pangalawang interval ay mas maliit. And they will sum up to definitely a smaller area than the original area that we had before the refinement of the partition inducer. Okay? And that is what is meant by this guy. All right? Actually, before nag-summing up pa, so ganun yung argument dito. So, nakwento ko na siya pero sinulat ni lecture notes yung proof in a formal way. Okay? Ginamit niya yung lemma 5.1, tapos isa-sum up mo lang naman yan. Hindi mo pala isa-sum up yan. Isa-sum up mo yan, maging equal siya dito, pero ito ay carried over there, and then isa-sum up natin to. That will be the upper Riemann sum, and then yung partition inducer nandito. So dito sa proof, ginamit niya muna yung lemma 5.1, alright, dun sa refinement. Tapos pinakita niya na dito sa bawat m sub I, which is from the original partition inducer, siya yung nandito sa dulo, tas kinuha niya yung summation. Alright? At yung summation na yon ay equal dun sa lower Riemann sum noong original partition inducer. Okay? Medyo pag tinranslate mo siya dun sa actual formal proof, medyo kailangan mo maging extra careful with the language. But you see, a geometric argument is much more, I would like to say much more reasonable or much easier to follow rather than just going through the text. Kaya talaga sa analysis, mas maganda yung nagdo-drawing. Kasi makikita mo talaga yung relationship nila sa isa't isa. Alright? But I hope you guys get the gist of the proof of lemma 5.1. And actually, it inherits the property of suprema and infima. Kapag ka kumukuha ka ng infimum ng isang subset, mas malaki yung nakukuha mong value. Right? Tapos pag kumukuha ka ng supremum ng isang subset, mas maliit yung nakukuha mo kaysa sa supremum ng mas maliit na set. Alright? So ganito rin yung argument for that. Okay? Now, what is lemma 5.24? Para siya dun sa susunod na lemma. And again, I said, hinati natin yung proof nito into several lemmas, though we could have written it as a single continuous proof. All right? I think the last piece in the puzzle to complete the proof of the inequality we desire ay yung lemma 5.3. Na kapag kumuha tayo ng dalawang magkaibang or dalawang partition inducers na posibleng magkaiba ng same interval AB, the lower Riemann sum with respect to the partition inducer P1 is less than or equal to the upper Riemann sum of F relative to the partition inducer P2. So what lemma 5.3 is telling us is that laging mas maliliit yung lower Riemann sum kesa sa mga upper Riemann sums kahit pa magkaiba yung partition inducers na ginagamit natin. Kasi kanina, yung mga inequalities nating dinevelop, parehas yung mga partition inducers. Madali siyang i-imagine kasi ano yung nangyayari? Kung same yung partition inducer, pag ginamit mo yung supremum as your height, definitely mas malaki yon kaysa dun sa rectangle na makukuha mo by using the infimum as the height. And then when you sum up larger numbers, compare it against with the sum of smaller numbers, laging mas malaking sum ng larger numbers. So it makes sense to compare them when you have the same partition inducers. But lemma 5.3 is telling us, hold on, that is not just the case. Mas generic yung property na kahit ano pang partition inducer yung gamitin mo, kahit magkaiba pa yung partition inducers, yung lower Riemann sums ay laging mas maliit kesa sa upper Riemann sums, regardless of what the partition inducer used for each of those sums are. Posibleng magkaiba. The proof is quite clever. It will use lemma 5.2. All right. So ang ginawa niya, kinonsider niya yung P1 union P2. Okay? Which again is a partition inducer ng set AB. After reordering the elements of P1 and P2 appropriately, pwede mo siyang magawang isang partition inducer. And P1 union P2 is definitely a superset of both P1 and P2. So definitely P1 union P2 is a refinement of both P1 and P2. All right? Tapos mag-start tayo sa isang inequality na alam na natin. Alam na natin na lower Riemann sum ni lower Riemann sum ni F relative to P1 union P2 ay mas maliit kesa sa upper Riemann sum ni F relative to the same partition inducer P1 union P2. Alright? Obvious tong inequality na to, right? Ito yung sinasabi natin na pag parehas yung partition inducer, obvious na mas malaki yung upper Riemann sum kesa sa lower Riemann sum. Alright? But we will use lemma 5.2 na yung lower Riemann sum ng isang partition inducer ay mas maliit sa lower Riemann sum ng isang refinement ng partition inducer na yon. But we know that P1 union P2 is a partition inducer of P1. So therefore, this lower Riemann sum would be greater than or equal to the lower Riemann sum of F relative to P1. All right? For which P1 union P2 is a refinement. Okay? And then, doon naman sa kabila, gagamitin ko ulit si lemma 5.2. Yung upper Riemann sum ng isang refinement ay mas maliit kesa sa upper Riemann sum prior to the refinement. Okay? Eh si P1 union P2 ay refinement ni P2. So, ibig sabihin, yung upper Riemann sum ni F relative to P1 union P2 ay mas maliit kesa sa upper Riemann sum ni F relative to P2. And then by transitivity of the less than or equal to relation, we have the desired inequality that the lower Riemann sum of F relative to a partition inducer P1 is less than or equal to the upper Riemann sum of F relative to the partition P2. Okay? So, kung isipin, parang when I was reading this, parang hirap tanggapin na kahit anong partition inducer, P1 and P2, laging mas malaking lower Riemann sum kesa sa upper Riemann sum. But the proof tells us na, yeah, medyo obvious pala siya knowing a property of, knowing lemma 5.2. Yes, Carlo?
Sir, just question, yung middle part, is that proven rin? But I know it's on the proof of 5.2, pero yung sa, if you go up, dun sa lemma 5.2, I think it says and instead of less than or equal. Yung between those two middle terms.
Okay. Now, I think you're referring to this one?
Yes.
Yeah. Ito I think na-prove na siya sa taas. Yung paggamit ng lemma 5.2 dito ay para dito. At saka para dito. Pero
okay.
tama ka, yung middle inequality ay hindi nanggaling sa lemma 5.2. Alright?
Okay.
I think nanggaling sa dito pa sa taas. Yun yung sinasabi ko na parang obvious yung property na yung lower Riemann sum ay laging mas maliit sa upper Riemann sum. I think we have that somewhere here. Sana tama ako, kundi magpo-prove tayo on the spot. Let's see. Now, there you go here. Nasa lemma 5.1.
5.1. Okay. Thank you.
pag parehas yung partition inducer, laging mas maliit yung lower sum kaysa sa upper sum. Tapos yun yung ginamit para doon sa
Okay.
middle
For
inequality.
the same partition inducer. Okay. Thank you.
Alright. Kaya mas maganda sana kung sinulat ko pala yung proof from scratch, no? Kasi kung sinulat ko yung proof from scratch, dito ka mag-start. Sabihin ko from lemma 5.1, yung lower Riemann sum ay mas maliit sa upper Riemann sum provided parehas yung partition inducer nila. Tapos unti-unti kong i-build up galing sa lemma 5.2 na, ay oo nga, ito ay mas maliit kasi refinement ni P1 si P1 union P2. And similarly for the other thing. Siguro it's a nice practice na rin na pag nagbabasa kayo ng proof, maganda yung comment ni Carlo na though one-liner yung proof, kung isipin nyo, ito ay mga ano lang yan, mga may masabi lang yung first sentence. It is basically a one-liner proof. Yan yung makikita nyo sa textbooks, makikita nyo sa websites, but it's a nice thing to rewrite it on your own way. Tingnan nyo kung, bakit nga ba ito nangyari? Right? It looks obvious. It's a one-liner proof. Pero yun nga, pag pinuntahan niyo yung nitty-gritty niya, makikita niyo na marami tong dinaanan. For the trained eye, it might be obvious, pero sa ating mga starters, siguro kailangan natin yung mga detalye sa gitna. And I expect you sa problem sets na kahit nakita niyo siya on the net, I'm perfectly fine with it as long as you put the effort to at least insert the details. All right? Now, other questions? Okay, so if there are none, then let's go to lemma 5.4. And I think this is the inequality that we are trying to establish here. Yung lower Riemann sum ay mas maliit, hindi na pala Riemann sum. Yung lower Riemann integral ay less than or equal to sa upper Riemann integral. And there's a glaring typo here. Dapat ito ay integral from A to B. Parehas yung bounds nila. Okay, pakibago na lang. Now, paano natin siya ipoprove? Gagamitin ko si lemma 5.3. Now, I will consider a partition inducer P, an arbitrary partition inducer of AB. All right? Tapos kukuha pa ako ng arbitrary partition inducers P prime. Pero sabi ng lemma 5.3, yung lower Riemann sum ni F relative to a partition inducer P, which was arbitrarily chosen, will always be less than or equal to the upper Riemann sum of F relative to any other partition inducer, say P prime. Ito yung ni-establish natin sa lemma 5.3. Yung lower Riemann sum ay laging mas maliit sa upper Riemann sum kahit na magkaiba yung partition inducers nilang dalawa. Ito yung hindi obvious mula sa lemma 5.1. Okay? So what have we said here? We are saying that LFP, right, the lower Riemann sum of F relative to the partition inducer P is a lower bound para sa lahat ng upper Riemann sums. Right? Kasi sabi natin siya ay less than or equal sa UFP prime for all partition inducers P prime. Hold on, guys. Okay, so ito, si P ay fixed for now. Though arbitrarily chosen, it is fixed. Lagi siyang mas maliit sa lahat ng upper Riemann sums, kahit ano pa yung partition inducer P prime. So we can say that L here, the L in the left, tawagin ko siyang L sub P, right? Siya ay isang lower bound para sa upper Riemann sum, sa lahat ng upper Riemann sum. All right? But what do we know about the upper Riemann integral? We know the upper Riemann integral to be the infimum ng mga upper Riemann integrals, upper Riemann sums. Okay? So siya yung infimum ng mga upper Riemann sums, so siya yung greatest lower bound. Pero si LFP ay isang lower bound. So therefore, this lower bound must be smaller than the infimum by the very definition ng pagiging infimum, yung infimum greatest lower bound. So definitely this guy will be less than or equal to the upper Riemann sum, being the infimum of all the upper Riemann sums. All right? So kaya meron tayong inequality na ito. All right, is that good? Now, again, I'm going back to my choice of P. Si P ay arbitrarily chosen from the beginning. Wala akong inimpose na property kay P aside from being a partition inducer. So si P ay arbitrarily chosen. Kahit ano pa yung P, lagi siya magiging lower bound ng UFP prime. Right? So ibig sabihin, totoo rin to sa lahat ng P. So what have we shown here? The upper Riemann sum is an upper bound for the class of lower Riemann sums. Ito ay upper bound para sa lahat ng posibleng lower Riemann sum ni F relative to P. Pero ano nga yung tanda natin? Yung lower Riemann sum, okay, siya yung supremum ng mga lower Riemann sums over P. All right? So siya yung supremum, so siya yung least upper bound. Pero alam natin yung upper Riemann integral ay isa sa mga upper bounds ng set of all lower Riemann sums. Siya na nga yung supremum. Siya na nga yung least upper bound. So kung siya yung least upper bound, tapos ito ay isang upper bound, therefore, ibig sabihin, totoo itong inequality na to. Right? Kasi nga, ito ay upper bound, pero pinakamaliit na upper bound ay ito, which is the lower Riemann sum. So therefore, the lower Riemann integral is less than or equal to the upper Riemann integral. Okay? So medyo masaya yung proof. Actually, nag-enjoy ako nung binabasa ko to na, clever application nung pagiging supremum at infimum nung set of all lower and upper Riemann sums. Okay? So, any questions? Nakita nyo ano to, no? Pagalingan ng pag-interpret. Hahanapan nyo talaga ng lusot kung paano nyo mai-interpret yung definition ng upper Riemann sum, lower Riemann sum, or upper Riemann integral and lower Riemann integral. Right? So, and then as promised, lemma 5.4 actually will give us um, an easier way, or will cut down our work into half whenever showing that a certain function is Riemann integrable or not. Kasi, di ba, kailangan nating ipakita yung equality ng lower Riemann sum sa upper Riemann sum to say that F is Riemann integrable. All right? So, usually you do it two ways. We prove that the lower Riemann sum is less than or equal to the upper Riemann sum, and the lower Riemann sum is larger than or equal to the upper Riemann sum or the upper Riemann integral. So sorry, puro integrals dapat yung binanggit ko. Now, lemma 5.4 already takes care of this guy. We already know that the lower Riemann sum is less than or equal to the upper Riemann. Mali na naman. The lower Riemann integral is always less than or equal to the upper Riemann integral. All right? So ito na lang yung kailangan nating i-prove kung gusto nating ipakita na Riemann integrable ang isang function via definition. We want to show that the lower Riemann integral is always greater than or equal to the upper Riemann integral for the function f. Okay? But I'm not saying that that is easy, because again, you still need to look at the supremum of all lower Riemann sums and compare it with the infimum of all upper Riemann sums, which is not a nice thing to do kasi medyo komplikado siya at marami kang kailangang computen. All right? And that's why, thankfully, we have established several criteria for Riemann integrability. And that's what section 5.2 is all about. All right? Now, yeah. Let's see the first integrability criterion. Theorem 5.1. A bounded function f is integrable on the closed interval ab if and only if. So, isa siyang magandang characterization kasi it worked both ways. If we know that it is Riemann integrable, then this condition will hold true. All right? And if this condition hold true, we know the converse is also true, that f is Riemann integrable. Right? So ano yung criteria na ibibigay ng theorem 5.1? Ang sinasabi niya is but f is should be a bounded function first, right? So a bounded function will be Riemann integrable if and only if sa kahit na nung epsilon, however small it is, there exists a partition P of the closed interval AB, or I think it meant here a partition inducer, P of AB, such that the upper Riemann sum minus the lower Riemann sum is less than epsilon. Now, it is like your limit definition. There is a challenge. The challenge is an epsilon greater than 0. Usually, we are looking for smaller and smaller epsilons, all right? And the response is, or the challenge for us, is to find a partition P so that the upper Riemann sum minus the lower Riemann sum is less than epsilon, right? Ano yung logic behind this criterion, okay? Kasi ang sinasabi niya ay kahit paliitin natin ng paliitin yung yung epsilon, all right? Lagi akong may mahanap na partition inducer ni AB nang ibibigay sa akin na upper Riemann sum minus the lower Riemann sum ay laging mas maliit kay epsilon. So ibig sabihin, palapit ng palapit yung upper Riemann sum sa lower Riemann sum. And if that happens, then that means that the infimum of the upper Riemann sums would be equal to the supremum of the lower Riemann sums, all right? Kasi nga less than epsilon siya for however small an epsilon we want, all right? So ibig sabihin, nagiging equal yung supremum at saka infimum na yon. And they will turn out to be, and that is essentially the definition for Riemann integrability. Okay? So let's try to see how the proof goes. Let's start first by proving, actually this should be the converse. So nag-start siya sa backward. So inassume niya muna na sa kahit anong epsilon greater than 0, we can always find a partition inducer P of the closed interval AB such that this is true. And we want to show that f, or the bounded function f, is Riemann integrable. Right? So how was it done? Ginamit yung definition ng, kasi nga gusto natin ipakita Riemann integrable siya, no? Ang tanging alam lang natin para maging Riemann integrable, upper Riemann integral ay equals to lower Riemann integral. Tapos dun sa assumption, meron tayong upper Riemann sum at saka lower Riemann sum. So we need to connect those two ideas, upper and lower Riemann sums and upper and lower Riemann integral. And one obvious property that we know between this corresponding pairs is that the upper Riemann sum is less than or equal to the upper Riemann sum, being the infimum. And similarly, the lower Riemann sum is greater than or equal to any lower Riemann sum, being the supremum of all such lower Riemann sums. Okay? So ito, definition lamang ng Riemann integrals being the infimum and supremum respectively. All right? So dahil ito ay papalitan ko ng, okay, so tingnan natin to. All right, I'll look at this guy. Okay. Iko-compare ko siya sa upper Riemann integral minus lower Riemann integral. Titingnan ko kung ano yung mangyayari. So, ko-compare ko ito at saka ito. Sabi nga natin, ito ay mas malaki kaysa rito. So, ito, pinalitan ko ng yung Riemann sum, pinalitan ko ng Riemann integral. So, all being constant, mas maliit yung makukuha kong sum, right? O makukuha kong total. Kasi yung mas malaking number, pinalitan ko ng mas maliit. So this guy apparently has a chance. So siguro palitan ko muna nito. Okay. LFP, all right? So yung minuend, pinalitan ko ng mas maliit na number. All right? So definitely this guy, this new number is smaller than the original guy. Right? Tapos, gagawin ko pa siyang ganito. Etong number na to, yung subtrahend, ay papalitan ko ng mas malaking number. Alright? So this will be replaced by a larger number. So mas malaki yung pinalit ko na subtrahend. So that means the new difference will be smaller than or equal to the original difference. So ibig sabihin, ito yung relation. Mas malaki itong original kesa dun sa sum ng mga Riemann as a difference ng dalawang Riemann integrals. But the original sum is less than epsilon. So by transitivity, this guy will be less than epsilon. Okay? But what do we know? This is true for all epsilon greater than 0. Dahil totoo siya sa lahat ng epsilon greater than 0 and the choice of epsilon is arbitrary, then necessarily the difference must be equal to 0. Alright? Ito yung isang lemma mula sa lecture notes 2 yata, na kapag ka meron kang number na less than kay epsilon, meron kang positive number, less than epsilon for all epsilon greater than 0, then that non-negative number must be equal to 0. Now, this is non-negative because the upper Riemann integral is greater than or equal to the lower Riemann integral by lemma 5.4. So this is a non-negative number. Less than all epsilon greater than 0, magiging mas maliit lang yung non-negative number na yon sa lahat ng epsilon na mas malaki kay 0 kung yung non-negative number na yon ay eksaktong equal kay 0. So therefore, we should conclude that the lower Riemann integral minus the upper Riemann integral minus the lower Riemann integral should be equal to 0. And there we go. Equality between the two Riemann integrals. And by definition, function little f is Riemann integrable on the closed interval AB. All right? Now, for the converse, okay, isusuppose naman natin na si f ay Riemann integrable. Right? Anong mahihita natin sa assumption na yon? Balik tayo sa definition ng Riemann integrable. So, alam natin kung siya ay Riemann integrable, equal yung lower at saka yung upper Riemann integral. Okay? Tapos anong gusto nating ipakita? Pag binigyan tayo ng kahit anong epsilon greater than 0, merong partition inducer P such that this inequality is true for all epsilon. Yan yung gusto nating ipakita. Alright? So, magbigay ako ng challenge. So, magbigay ako ng epsilon greater than 0. Tapos, kung matatandaan nyo, on the chapter, when we talk about suprema and infima, may property or may magandang characterization yung infima at suprema with respect to an arbitrary epsilon greater than 0. Okay? Now, by the fact that the upper Riemann integral is the infimum of all upper Riemann sums, okay, siya na dapat yung greatest lower bound. Again, ito yung greatest lower bound ng mga u. So pag dinagdagan ko siya ng katiting na number na positive, say epsilon over 2 for any given epsilon greater than 0, etong bagong sum na to, hindi na siya pwedeng maging lower bound. Kasi ito na nga yung pinakamalaking lower bound, yung upper Riemann integral. Dinagdagan ko pa siya ng katiting, epsilon over 2. Siya na nga yung greatest lower bound. So ito, hindi na siya pwedeng maging lower bound. Kailan siya hindi nagiging lower bound? Kapag siya ay mas malaki na sa isang upper Riemann sum. So that's why we say that, okay, dahil siya yung infimum, there should exist a partition inducer P1, all right, such that this is true. All right? Na pag nagdagdag ako ng katiting, hindi na siya lower bound. Okay? Kasi nga, ito ng Riemann integral, yung greatest lower bound. And then similarly, ganun din yung mangyayari dun sa pangalawa. All right? Gagamitin ko naman yung definition ng pagiging supremum. And I think may baligtad dito na inequality. All right? Let's see. Ito ay yung lower Riemann sum. So ito yung supremum ng mga lower Riemann integral, right? Dahil siya na yung siya yung supremum ng mga lower Riemann sums, right? Siya yung smallest, siya yung least upper bound. Siya yung least upper bound ng lahat ng mga lower Riemann sums. Pag nag-minus ako sa kanya, ng kahit na napakaliit na positive number, hindi na siya magiging upper bound. Alright? Hindi na siya magiging upper bound kasi siya na nga, yung Riemann integral na nga yung pinakamaliit na upper bound. So therefore, hindi na siya magiging upper bound. Anong ibig sabihin pag hindi siya upper bound? Ibig sabihin, merong isang lower Riemann sum na mas malaki sa kanya. And that's why we can say there exists a partition inducer P2 of AB such that the lower sum relative to that partition inducer P2 is greater than or equal to dun sa lower Riemann integral minus epsilon over 2. Okay? So, yun yung idea. Tapos, ano nga yung gusto nating i-prove? Yung U minus L dapat ay less than epsilon. So, I'll just take U minus L. All right? U minus L. We'll get this guy. And let's see how it relates to the upper and the lower Riemann integral. So, this guy minus this guy. All right? So, tapos ito, papalitan ko ng mas malaki. Ma-minusan ko siya ng mas maliit. So, ibig sabihin yung bagong difference na makukuha ko ay mas malaki. Alright? Ang ginawa ko kasi ito, pinalitan ko ng something larger. So, mas malaki yung minawin. Tapos, mas maliit pa yung subtrahend. Right? So, therefore, the new difference that I get will be larger than the original difference we had before. Okay? So, ito yung bagong difference na sinasabi ko. And then, what do we have here? Well, upper Riemann sum minus the lower Riemann sum. But our assumption is that f is Riemann integrable. Therefore, the upper and the lower Riemann sums are equal to each other. So, this guy minus this guy is just 0. Tapos dito papasok, sir, bakit mo pinili na epsilon over 2? Pwede namang epsilon na lamang. Gusto ko kasing makuha yung less than epsilon. Na-anticipate ko lang na magkakaroon ako ng plus epsilon dito, tapos minus negative epsilon over 2. Alright? So the total of that would be epsilon over 2 plus epsilon over 2 equal to epsilon. And so now, we can say that we have u of f of p1 minus L of f of p2 is less than epsilon. Tapos, gagamitin ko yung refinement property. Pag gumamit ako ng isang refinement, tawagin nating p sub epsilon. Siya si p1 union p2. Now, yung partition inducer, let's see. Okay, tingnan natin to. So, alam na natin ito ay totoo. Kaya lang ang sabi nung theorem, dapat there exists a partition P such that the upper Riemann sum of that partition P minus the lower Riemann sum relative to that partition inducer P must be less than epsilon. Dito nakuha natin magkaiba pa yung partition inducer. So gagamitin ko yung lemma 5.3, right? By considering the refinement P epsilon, which is P1 union P2 of P1 and P2. All right? Siya yung magiging response ko dun sa arbitrary challenge epsilon given earlier. Right? So we know this guy, but we know that the upper Riemann sum of a refinement is smaller than the upper Riemann sum of the original partition inducer. And the lower Riemann sum of a refined partition is greater than or equal to the lower Riemann sum of the original partition, thereby establishing this inequality over here. But again, we knew that this is less than epsilon, so we are forced to accept that this is also less than epsilon. Okay, which ends the proof. Given tayo ng epsilon greater than 0, nakahanap tayo ng isang partition, namely P1 union P2, such that this is less than epsilon. End of proof. Okay? So now, it suffices to show that kahit anong epsilon less than 0, lagi tayong may makikitang partition inducer such that the difference between the upper and the lower Riemann sum ay laging less than epsilon. So medyo gumaan yung trabaho natin kasi instead na computean pa natin yung supremum at infimum ng mga lower at upper Riemann sums para lang ma-compare kung equal yung upper saka lower Riemann integral, pwedeng maghanap na lamang tayo ng isang partition inducer para sa isang specific epsilon greater than 0 and check the difference between the upper Riemann sum and the lower Riemann sum with respect to that partition inducer and see if that would be less than epsilon. Okay. Now, let's illustrate how this is used using example number 6. So dito, ipapakita natin na yung linear function ay Riemann integrable. I think I mentioned last time na napakita natin na Riemann integrable ang isang constant function. Tapos sinabi ko na baka ipagawa ko sa problem set ay yung linear function ay Riemann integrable. Unfortunately, nandito pala siya sa example 5.6, so I need to take my word back on that. So, iba na lang ibibigay ko sa inyo sa next problem set. Okay? But let's see how this criterion is used in order to establish the Riemann integrability of the identity function f of x equals x. Then from here, you can just use properties of integrals to show that any arbitrary linear function ax plus b is also Riemann integrable. Okay? Now dito, gagawin natin yung partition inducer muna. So i-consider natin yung partition inducer P to be this partition inducer, P sub n, comprising of I over n, I going from 0 until n. So ang itsura nitong partition inducer P sub n ay 0, 1 over 2, 2 over n, and so on until n minus 1 over n hanggang kay 1. So isa siyang partition inducer. Alright? Isang specific partition inducer. Tapos mapapakita natin na itong choice of partition inducer na to can give us the desired partition inducer response to the arbitrary challenge epsilon later. Alright? But to see how that works, tingnan natin ano yung upper Riemann sum of f relative to P sub n minus the lower Riemann sum of f relative to P sub n is with respect to the parameter n. Okay? So, insert tayo dito ng ilang mga detalye. Yung upper Riemann sum ay summation ng m sub I times delta x sub I by definition of the upper Riemann integral or upper Riemann sum minus summation ng infima, which is denoted by m sub i's times delta x sub I. So definition ng upper at saka lower Riemann sum. And then property ng summation, same index lang naman to, over all i's. Pwede ko itong isulat in terms of a single summation. So pwede siyang masulat as summation over I ng mi delta xi minus little mi delta x sub I. All right? And then delta x sub I is a common factor between the two terms inside the terms in the summation. So I can factor out delta x sub I and get this line. All right? And then, ano ba yung suprema m sub I at ano yung infima m sub I sa mga subintervals na nandun sa partition inducer. All right? Remember, our function is f of x equals x. So sa isang interval x sub I hanggang x sub I plus 1, ito yung itsura ng graph niya, right? The suprema occurs at the right endpoint. The supremum resides at the right endpoint, while the infimum resides on the left endpoint, right? So dun sa dun sa given interval, ang supremum ay yung x sub I, alright? Function value siya sa kanan. That pa lang ginawa ko ay x sub I minus 1 versus x sub I, alright? Function value sa kanan, pero ang function value sa kanan ay f of x sub I, which is x sub I. So that's how you got that substitution. And then the infimum, m sub I, is the function value at x sub I minus 1, but our function is the identity function, alright? Kaya naging x sub I minus 1 naman siya doon. Okay? And then x sub I minus x sub I minus 1 is basically delta x sub I. That's the length of the ith subinterval. And hence, we can simplify it to be the sum of delta x sub I quantity squared, I going from 1 to little n. Okay? Tapos, alam naman natin kung ano yung size ng bawat subinterval. Kasi nga, ito yung partition inducer natin. Regular yung pagkakapartition, meaning bawat partition ay magkakasing haba. So that would be x sub I minus x sub I minus 1. So that could be 2 over n minus 1 over n. Or you can do that between any two consecutive elements of the partition inducer. What you'll get is 1 over n. Okay? Or when you square that, you're going to get 1 over n squared. Tapos si 1 over n squared ay constant with respect to I. Ang index ng summation ay I. So yung 1 over n squared ay pwedeng lumabas ng summation. So magkakaroon na lang tayo ng summation ng 1 starting from 1 until n. So ibig sabihin dito, nagsasum up lang tayo ng n na mga 1s. So 1 plus 1 plus 1 plus 1 n times. So this total will be little n times 1 over n squared outside will give us 1 over n. So in summary, what we have shown here is that the upper Riemann sum minus the lower Riemann sum is equal to 1 over n. But as n grows very, very large, this guy will go to 0. And so we say that this difference converges to 0 taken as a sequence with respect to n. So ito, sequence ng upper Riemann sum minus lower Riemann sum ay nagko-converge kay 0. And by definition of convergence of a sequence, given any epsilon greater than 0, there exists a capital N element of the set of natural numbers such that capital N is greater than 1 over epsilon, such that if, dapat ito ay may if, okay? Medyo kakaiba pala yung wording, no? There exists a capital N greater than 0. Pwede ito ay that is, right? Capital N must be greater than 1 over epsilon kasi ang challenge dito ay epsilon na naman. Ang challenge ay si capital N dun sa definition ng convergence ng sequence, all right? Now, by the Archimedean property, you can always find a natural number n that is greater than 1 over epsilon, however small epsilon is, all right? So that means this guy will always be less than epsilon. And by the integrability criterion, theorem 5.1, the constant function or the identity function is integrable on a closed interval 0 to 1. Okay, so this is a nice exposition on how to use theorem 5.1 to check for convergence. Sorry, not convergence, Riemann integrability. All right. Now let me see if I'll have enough time to talk about theorem 5.2. And yeah, I think so. If not, I'll borrow probably 5 more minutes if hindi ko siya matapos on time. These are another criteria for Riemann integrability, pero one way lang. All right? So, ito ay mga sufficient conditions. Ano yung mga conditions na kaya nilang i-imply yung Riemann integrability? Kasi nga, malaking question sa atin, kailan siya nagiging Riemann integrable? So we are actually more after the sufficient conditions. Ano yung mga properties that ensure Riemann integrability? And theorem 5.2 gives us 2 other things, and I think these are easier to apply than the definition of Riemann integrability or theorem 5.1. So kailangan nating magsimula sa isang bounded function f, defined on the closed interval 0, 1. Actually, not necessarily 0, 1, pero pwede siya sa interval AB, a generic closed interval AB. Right? May dalawang sufficient conditions. Una, kapag ka si f ay continuous sa AB, so dalawang property yon, boundedness and continuity on the closed interval implies Riemann integrability. Then another sufficient condition is boundedness plus monotonicity. Kapag ka monotonic yung function mo, kapag ka siya ay bounded sa closed interval, then automatically we know that it is Riemann integrable. No other questions asked. So napakasaya ng Theorem 5.2 kasi madaling i-prove ang continuity at saka monotonicity relative to showing Theorem 5.1 or showing Riemann integrability by definition. Okay? Now, silipin natin yung proof ng Theorem 5.2. I don't think it is that difficult. Pero ito na naman, gagamitin ko yung Theorem 5.1 but I will be clever about it. Tingnan natin kung paano siya ginawa. Now, let's consider a continuous function on closed interval AB. F is known to be bounded, all right? Now, we have a theorem from before that if your function is continuous on a compact set, such as a closed interval AB, then it is automatically uniformly continuous on the closed interval AB. So there you go, I used that. I don't know if it's somewhere in the lecture notes on uniform continuity or from the problem set. So I just don't remember, but there is a result saying that, okay? And dahil siya uniformly continuous, sa kahit na nung epsilon na ibigay sa atin, lagi tayong may mahanap na delta greater than 0 such that sa kahit anong dalawang elements x and y of the closed interval AB, such that they are within delta units from each other, all right? Yung absolute value ng difference ng function values nila ay laging mas maliit sa epsilon over b minus a. Theoretically, this should have been just epsilon, standing for an arbitrary positive number. Pero si epsilon ay arbitrary, okay? Si b minus a is constant. An arbitrary number divided by a constant is still an arbitrary number. So instead of an epsilon, I am choosing the challenge here in a clever way. So gagawin ko siyang epsilon over b minus a. And you will see later bakit gusto ko siyang epsilon over b minus a. Bakit hindi na lamang epsilon? All right? Now, to show integrability on the closed interval AB, we can borrow Theorem 5.1. We want to show that the upper Riemann sum minus the lower Riemann sum will be less than epsilon for some partition P of AB. Gagamitin ko yung Theorem 5.1 to establish Theorem 5.2 Part A. Okay? Now, paano ko siya gagawin? Ngayon, gagamitin ko yung pagkakaroon ng delta, alright? Na response dun sa challenge na epsilon over b minus a. Now, I will choose my partition P na kailangan para sa Theorem 5.1 to be a partition inducer such that the delta exabytes, or the difference between two consecutive elements of the partition inducer, is less than delta. The delta that we have gotten from the epsilon challenge dun sa uniform continuity. All right? Now, f is continuous on the closed interval AB by assumption. So therefore, it must be continuous on the closed interval or actually on any closed subinterval induced by the partition inducer P. So magiging continuous siya dito sa subinterval na to na nabigay sa atin ng partition inducer. Okay? Dahil continuous siya, ito ay isang compact set by Weierstrass's theorem, f attains its maximum and minimum, x sub capital Mi and x sub little mi respectively. Alright, so meron siyang maximum at minimum at na-attain siya ni function f sa dalawang numbers dito sa interval na to. Tawagin natin yung mga numbers na yon ay x sub capital Mi at saka x sub little mi. Wala dapat siyang brackets. Alright? So, dahil pinili natin itong interval na to ay of length delta or length smaller than delta, si x sub I, x sub I sub I, at saka si x sub little m sub I ay parehas nandito sa interval na to. So, ibig sabihin yung distansya sa pagitan nilang dalawa ay mas maliit din sa delta.
Kasi ito si x sub I minus 1, ito si x sub I. Yung distance nila ay mas maliit kay delta. Posibleng nandito si x sub capital MI. Nandito si x sub little mi, kunwari. Basta nasa loob sila nung interval. So, ibig sabihin, yung pagitan nilang dalawa ay obviously mas maliit kay delta. Right? Kasi yung buo less than delta. So, sila dapat less than delta rin. So, we have this. So, ibig sabihin, ano yung masasabi natin? Now, the condition, right? Siguro pwede ko na itong burahin. Okay? Yung function value dito minus yung function value dito dun sa definition ng uniform continuity, function value at x, function value at y, whenever x and y are within delta units from each other, will be less than epsilon over b minus a. We already knew that x sub m sub I and x sub little m sub I are between delta units apart from each other or less. Ibig sabihin yung function values nila dapat mas maliit kay epsilon over b minus a. Ginamit ko yung nandun sa uniform continuity. All right? And then let's see what happened next. Oh, remember this is m sub I. And this is m sub little m sub I, right? Kasi sila yung maximum at minimum over that subinterval. So pag kinuha natin yung upper Riemann sum relative to P minus lower Riemann sum relative to P, ito by definition, yung difference na yan, actually na-derive na natin siya kanina to have this form. Maxima minus minima times the length of each of the subintervals. All right? Now, ito, alam ko na ito ay laging mas maliit. Yung capital MI minus little mi ay laging mas maliit sa epsilon over b minus a. So, pwede ko siyang palitan ng epsilon over b minus a and get a smaller number. Actually, it is a strictly smaller number. Tapos, ito ay constant. So supposedly, meron ka dyan delta x sub I summation. Ito ay constant with respect to the index of the summation. So yung epsilon over b minus a can jump out of the summation and we'll get this guy. All right? Pero ano itong summation ng mga delta x sub i's? Sila lamang yung sum ng haba ng mga subintervals. Pero alam natin, yung subintervals form a partition of the interval AB. So pag kinuha natin yung union ng mga subintervals, makukuha natin yung AB. At dahil partition sila ay disjoint. So pag sinum up ko yung haba ng mga delta x sub i's, I will get yung haba ng original interval AB, which is b minus a. And that is why I wanted the challenge epsilon over b minus a dun sa definition ng uniform continuity because na-foresee ko na dito sa proof na to, kailangan magmumultiply ako later ng b minus a. So kaya ang pinili kong challenge doon sa uniform continuity ay epsilon over b minus a so that after everything is done, it will boil down to epsilon over b minus a times b minus a. And that will cancel out to give us epsilon. And so in summary, we have found a partition inducer P such that the upper Riemann sum minus the lower Riemann sum, both relative to the same partition inducer P, is strictly less than epsilon. So for any epsilon greater than 0. And so I will invoke theorem 5.1 and say na, okay, by theorem 5.1, we have f is Riemann integrable. Okay, and that proves continuity is sufficient. Continuity of a bounded function on a closed interval AB is sufficient to conclude that the function is Riemann integrable over the closed interval AB. Okay. Now, any questions about that proof? Medyo marami lang nangyari, no? So, but I hope the idea is fine. Okay. Now, the proof for part B, here the assumption is that f is monotonic. Yung case when f is increasing is given in the lecture notes. When f is decreasing, you will have a very analogous proof. Medyo babaliktarin nyo lang yung ibang inequalities, but essentially that's the same. All right. So, yeah. Actually, mas generic yung proof ng part A. Kasi sa part A, inassume lang natin continuous siya. Hindi natin alam kung nasaan yung supremum doon sa bawat subintervals. Pero kung si f ay monotonic increasing, alam natin na yung maximum laging nasa right endpoint at saka yung minimum ay laging nasa left endpoint. Alright? So you can bank on that idea and then modify the proof from part A to get the proof for part B. Kasi alam mo na saan nagaganap yung maxima at saka yung minima sa bawat subintervals. Alright? So probably I'll leave part B as a reading assignment to you guys. And then probably let's look at example 5.7 when we go to when we start our meeting on Tuesday. All right. Tapos medyo kailangan kong ayusin yung proof ng theorem 5.3. Ito yung sinabi ko na medyo may mga typos at naiwan na detalye. Katulad nito, hindi ko alam kung ano yung ni-union. So kailangan kong either i-reconstruct yung proof or hanapin yung proof ni Abbott. Kasi I think yun yung sinundan nito. So I'll see which is better, me writing the proof from scratch or just correcting this using Abbott's proof, right? Kailangan ko pa maghanap ng kopya ni Abbott. So yeah, I'll try to check that. And we'll start with example 5.7 next time, all the way to theorem 5.3, and hopefully start with some of the properties of integrals. And then after that, we'll talk about the fundamental theorem of calculus, all right? Any questions, guys? Okay, di ko pa kayo nakakumusta about the problem set nga pala. Di ko pa siya, meron lang ako nag-grade na konti, pero I think that's just one or no, that's about 3 papers that I have checked. So pakiantay na lang uli. And then, yeah, I might not be able to finish everything before December 16 kung kailan lalabas yung problem set, but I will include some questions dun sa feeling ko matatapos ko by December 21. So there might be some problems that you will see on December 16th that are not yet discussed. So yung discussion nung mga topics na yon ay posibleng nasa December 21 ko pa mabibigay. Alright? Doon ko pa ma-deliver. Or pwede ko rin namang i-record, depende kung ano yung mangyayari sa atin next week. But I hope I'm not too optimistic na matatapos ko siya by December 16. So either I'll record or we'll have classes on December 21st para ma-cover ko lahat ng coverage nung problem set number 4. Kaya lang pala December 21, baka gusto nyo tapusin by December 21 para wala na kayong baon sa holiday break. But let me think about that if I'll just record a lecture after December 16, but before December 21. Okay? All right, so any concerns, guys? Okay, kung wala na, so thank you guys for coming today and for bearing with me. Medyo, I think, mabilis yung discussion, but I hope you had fun, or at least you pick up some things, even the little things here in the proof or in the discussion. And enjoy your weekend, guys. Let's see each other again on Tuesday. Bye, everyone.
Thank you.